Hello class, this video is a recording of how to work through problem number 4 in lab 2. And so I've had a few questions about how to kind of get started and getting kind of tripped up on this machine language, this Vole architecture. And I just wanted to take a minute to work through a problem just to kind of help you guys get started. Most of the problems on your lab are going to be very similar to this one as far as the techniques required to solve it. So yeah, let's jump right in. Well, actually, before I jump right in, I want to say it's important that you read the chapter before watching this video. The chapter breaks down how to interpret instructions and just kind of the role of the CPU, and it's some really great information in there. So I recommend you read that and check out the information on the in the lessons folder in Blackboard. So, problem 4 says the following table shows a portion of a machine's memory containing a program written in language described, in the language description table. So the one we're referring to. So things to note, this is the main memory. So the problem says here's our main memory. This should hopefully make sense to you guys, since the main memory always holds the main program. According to the book, that's where the program lives, in the main memory. Something that's easy to get tripped up, but the register is actually a completely separate place to store information. It's a much smaller memory space, so there's a lot fewer things you can store in there. However, it looks very similar to the main memory. It's completely different. The book has some great diagrams to help you kind of separate the two mentally. So before starting, I recommend always having some sort of table written out on either a Word document or a scratch piece of paper, just so you can kind of keep track of the values that are going to be in the register. So let's jump right into it. I've got the instructions listed out here, and here we go. So I'm going to be using the table at the very beginning. This is also in your book, and your job is to take every instruction, interpret it using this table, and pretty much do exactly as it tells you to do. So first instruction has an opcode of 1. That's your first digit there. So we're looking at this first opcode here, and it says to load the register R with the bit pattern found in the memory cell whose address is XY. So that's kind of a lot there. Let's unpack what that says. So first step is to load the register R with some bit pattern. So first off, what is register R? The way we find that is by matching up the next 3 digits in our instruction. And we do that using the pattern given on our opcode, whichever one we're on. Here the pattern is RXY. So R is going to be C, since it matches up with the second place, and XY is going to be digits 3 and 4, in our case 0, 3. So if you want to, you can say R is going to be C and XY is 0, 3. Let's hit CY. XY is 0, 3. Okay, so writing that out, load the register C with the bit pattern found in the memory cell whose address is 0, 3. Please excuse my poor typing. Okay. So we still don't know the bit pattern because this says to load register C. So register C down here is going to be loaded with something with the bit pattern found in the memory cell whose address is 0, 3. So now we're referencing back to our main memory. So let's go back to our problem and see what's at that memory cell. Memory cell whose address is 0, 3, address 0, 3. I'll move that over. But address 0, 3 has a content of 0, 3. Okay, well that is a coincidence, but let's keep going. Next instruction says load the register R with the bit pattern XY. So this one's a little easier. Same thing, match up your R and XY. In this case, R is B, XY is, well, 0, 3 again. Let me make sure that I wrote that down correctly before. Yep, okay. So this says load the register B with the bit pattern 0, 3. So this is telling me that here's my bit pattern. I don't have to do anything else. So now I know address B has a bit pattern of 0, 3. All right, let's continue. Next instruction, 5ABC. So 5 is an add command. Add the bit patterns in registers S and T as though they were 2's complement and leave the result in register R. So I'm going to line up the letters here. So this says add the bit patterns in registers S and T. Well, in this example, S is B and T is C, since B is the third digit, just how S is the third digit, T is the fourth digit, C is the fourth digit. So I'm just matching up this pattern from my instruction to what the opcode is expecting. Okay, so add the bit patterns found in these two registers. So we know what those two are. Each one has content of 0, 3. So our job is to add 0, 3 plus 0, 3 and get some result. Well, before I can do that, 3 plus 3 is not 6 in this case, or it's not quite that simple. It might not always be that simple, because this is actually hexadecimal. So in chapter 1 we talked about what hexadecimal is. So before I can add these, I'll need to convert this to their binary form, because this isn't the 3 that we're all used to in our decimal number system. This is actually hexadecimal. So before I can proceed, I'll need to convert 0, 3 to binary, and you can refer back to chapter 1 for that, but that would be 0, 0, 0, 0, 0, 1, 1. So now I can add these two together. So 0, 0, 0, 0, 0, 1, 1, plus, let's add in a couple of spaces here, 0, 0, 0. We happen to be, okay, and we can add a little underlining here to make it look a little, there we go, like we're adding. And so 0, oh, my underline is still going, is it? Sorry about that. So we know 0 plus 0 is of course 0. So let's figure out what we're going to do here. So 1 plus 1 is 0. Carry the 1. This is really hard for me to show what's going on here, but so I have 1 plus 1 is going to be 0. Carry the 1. So that's why I wrote a 0 down here. And when I carry that 1, I'm going to have 1 plus 1 plus 1, which is 1. That would carry another 1 to this third column, and then 1 plus 0 is 1. So I know that's kind of hard for me to show on this Word document, and I apologize for that. If you're kind of confused about how I did that adding, feel free to reach out to me. I can work something out on a scratch paper or point you to some more resources to help you out with that. So our last step, I know this seems like a lot, but we need to convert this value, this binary value, back to hexadecimal. And the way we would do that is by looking at these separately, but refer back to chapter 1 if you need some help on that. So the hexadecimal value would be 0 and 6. So in this case, 0, 3 plus 0, 3 did turn out to be 0, 6. And that's because for really a very simple reason, these values are so small, but that's not always going to be the case. So if you do this, I do recommend converting it to binary, adding, and then back to hexadecimal. That would be the correct way to do that. Let me add some spacing here. Okay, and so we're still not finished because the instruction said to add the bit patterns. Well, we added them, we got the result. But then it also says to leave the result in register R, and register R is, for us, A. Because A is the second value in this instruction, and R is the second value. So down here we need another address. I'm running out of room. Well, it doesn't matter that they're not in order. Address A now has the content of 06. Okay, so let's continue. Last thing we need to do is store the bit pattern found in register R in the memory cell whose address is XY. So store the bit pattern found in register A. So A aligns with R, since it's the second digit here, second value in my instruction. In the memory cell, whose address is 00. So now we're actually storing that bit pattern. So the bit pattern found in register A, that's what we just calculated, so 06, in the memory cell whose address is 00. So this is where it can get really tricky, because now we're not actually storing something in the register, we're storing something in a memory cell. So when you see the word memory, light bulb should go off. That's the main memory. So I'm actually changing the content at address 00. So that is no longer 1C, that is going to be 06, which is this value from register A. So the last instruction is the halt command, and our program is finished. So let's answer the questions. What bit pattern will be in register A when the machine halts? Well, that's of course 06. All I have to do is look at register A, 06. What bit pattern will be in the memory cell? 00 when the machine halts. Well, that's also 06 because I can look up here at 06. If you have any other questions on this, feel free to reach out to me. This is very tedious and can sometimes be easy to get yourself confused. So yeah, reach out to me on Teams or email, whichever works for you. Thank you.